So, good afternoon, and thank you for this nice introduction, Dimitri. So I need to make a couple of things clear because I could end up in jail if I don't correct some of things you have said about me. So I am working for Hysteresis, which used to be called Semaglace, which is a kind of water problem institute, but not from the French Academy of Science, from the Ministry of Agriculture. And I'm working there at the deputy scientific director, not the deputy director.
If so it's much higher than
it's much lower. Science in a scientific institute is the bottom. It's a very secondary matter, of course. No, of course not. But so I'm only the deputy scientific director for hydrology and hydraulics. And then I'm not going to speak in Russian. I'm going to speak in English with a French accent. Okay? So the first thing I would like to explain is that I was told that this was a school for young scientists, and I imagined to prepare something like a lecture. It's not research. It's not research. It's result. It's seen as a lecture. So maybe you will consider that I am going too slow. That I am speaking about too simple things. If so, just please wave your hands and say we know all that, and I will go faster. Okay. Second, I was also, when we were discussing the program, offered to make suggestions. So I was offered to make these suggestions with a of this lecture with a very strange name. First, it starts with simple. Simple, usually in science, you don't claim that you are doing simple things. You claim that you are doing complex things. And that's how you impress your colleagues. So, but I've always been interested in simple methods. It's mostly because that's the way I learned hydrology in Hysteresis. The old engineer who taught me everything I know in hydrology was fond of simple methods. If a method was not good enough until you could not simplify it further for him. So this is something like genetic. We are all the produce of our education, so I'm also the produce of a certain kind of education. And then I thought that with a lecture just after lunch, starting with simple, I will have no attendance at all. So that's why I decided to use an intriguing word, elasticity of streamflow for climate. So that's a compensation for talking about simple things. So the first question, so we should ask ourselves, is what is elasticity? This is a question I ask you.
They're not economists.
So if you are a physicist, you should think that elasticity is the study of forces and spring. But this is not what we want to discuss. And in fact, elasticity comes from economics. In economics, so elasticity, this is a measurement of how an economic variable is responsive to a change in another variable. So, and it's usually a ratio in percentage. So what you can read in the economic literature is you can read about the price elasticity of demand. So what is the price elasticity of demand? If demand changes by 20%, according to market laws, you know that economics is guided by some invisible hand. you have to believe in that if you study economics. Adam Smith wrote about it. So he's a god of economics. So how price will change when demands change? How much percentage price rise or decrease you will have when demand moves? Okay. So basically, elasticity is a kind of sensitivity. So if elasticity is equivalent to sensitivity, why didn't I use the word sensitivity? Well, I have two reasons. The first reason is that elasticity it looks fashionable, it looks a little mysterious, and it attracts attention. The second is that there was a famous US hydrologist called John Sharkey who started to use this word 30 years ago or more. That's I think the paper where he starts to he used the word elasticity first. So now that I have a reason for using the word elasticity instead of sensitivity, why did I use simple this word simple? Because Professor Kristanova told us this morning about models which are, and I guess she did not include the most complex, but the models that were tested in this intercomparison were all distributed complex models. So if we want to know what the future will be according to climate change, we need distributed, physically based representation of catchment processes with many million of cells, many layers, many everything. We need inputs, we need parameters, and we need huge computers. That's a way to give an answer concerning the future of stream flow, the future of hydrological flows in a changing climate. But as I've been educated in an environment where we were not looking these very extremely complex models favorably, I wanted to present something about a much simpler approach. And after all, we could consider that climate change is a kind of experiment that humankind is making with the whole globe. So, involuntarily, probably, but that's an experiment we make. But by doing this experiment, and we don't know the outcome, we don't know what will happen, and we would like to predict to some extent, basically we could just look at nature. Mother Nature is also making experiments of her own. And what I would like to present is our experiments, how to use the experiments that Mother Nature is performing. For example, what kind of experiments am I talking about? Some of you have heard about millennium drought in Australia. In fact, Australia, when you heard about Australian climate, is either a tremendous drought or a tremendous flood. They don't have average climate there. But they had this millennium drought that lasted from 1997 to 2009, and when you look at what it produced as drought, it produced, according to some climate projections, a climate equivalent to the worst case 2050 scenario. So they already have the answer. They don't need any model to know what will happen because they experienced it for a while. If you look at long-term time series here of precipitation, here precipitation are represented as anomalies. So anomalies is precipitation of the given year minus the average precipitation. And this is the Sahel precipitation anomaly, so you all know where the Sahel is. It's the lower dry African climate below the Sahara. And there have been large droughts in the 70s and the 80s. And if you look at the precipitation anomaly since 1900, and you can see that there have been periods of prolonged excess of rainfall, periods of prolonged lack of rainfall. So nature is experimenting with the climate, and if we are able to look at the consequences of those long periods, maybe we can deduce what the future of the Earth will be. And same for the contiguous United States. This is, and I wanted to produce the same plot for France. I did not have time, but I could have made the same. You can see droughts don't come necessarily completely randomly. They come in aggregate, and they of course they will have very interesting consequences. And we could look, if we have measurements, we could just look at them and try to reduce things. So, and so the question I would like to deal here with is that what kind of predictions could we derive from hydrological data, and without any model? And of course, we will have an idea of the uncertainty of our prediction. So, I wrote without model, and so you don't know me, but I'm a modeler. So, a modeler that says that he will, claims that he will do something without model is of course lying. That's why I put I don't know quotes around without, but almost without model, we would like to be able to give predictions. And that's the first question I want to address here. And the second question is, okay, if we don't have data, what could we do with the simplest of the hydrological models that many of hydrologists don't even call models, they just call them formulas. So we also have alternatives with a little bit of formulation. Okay. So, and then let's look how we could compute this hydrological elasticity and use it to predict the impact of meteorological changes on the hydrological cycle. So, mathematically, what elasticity, as I told you, is a ratio. So, if we call Q is quite widely used as for streamflow. So, the anomaly, the change of Q divided by the average Q, and we try to relate it to the change of some climatic variable X divided by the average climate of X. So this is what the economists call elasticity. So they, instead of Q, they put the price of the goods, and instead of X, they put the demand or anything else. So this epsilon, it is what they call the elasticity. So epsilon, it has nice properties. It's non-dimensional because it's a ratio between two already non-dimensional quantities. So that's what I want to derive from hydrological data. In fact, there is a almost equivalent definition, which is even simpler. That will also yield non-dimensional elasticities or sensitivities, because in hydrology we are used to compute or to evaluate is not the right word.
Calculate?
not even calculate. It's we express. Can you say express? We are used to express stream flow in slightly non-dimensional terms. So stream flow is computed in cubic meter per second, but as hydrologists, we want to make things independent from the size of the catchment. We transform the cubic meter per second into millimeter per year, millimeter per. Okay, the engineers always have a problem when I tell them that the discharge is expressed in millimeter. But when we do water balance, that's what's simplest. And if X, for example, if it's precipitation will also be in millimeter. So this will be a completely non-dimensional ratio. If we use, instead of course with temperature, it will not work. If with temperature, we will have millimeter and degrees Celsius, it will not work. For temperature, we need to use these relative ratios. But if we transform temperature into potential evapotranspiration, so with there are many formulas for that. They are all wrong, more or less. They're all good, depends how you look the glass, half full, half empty. But if you use, at least, if you want to know the sensitivity of discharge to either potential evaporation and precipitation, you can use just this expression. It's even simpler than the other. And of course, there is a relation between E and epsilon if we know those two equations. Okay? And so, don't forget, I will not show you results with that when we say stream flow, we are not forced to consider that it's average stream flow. We could use some stream flow characteristic. It could be a quantile of stream flow. It could be a flood quantile, a low flow quantile, everything. We could even try to introduce them in these equations and see what it produces. Okay? So to summarize, there are two ways to discuss the sensitivity of stream flow data or stream flow derived data. One is relative, the other is absolute. The tradition is to call elasticity the relative one and sensitivity the second one, but I will call elasticity both of them because I am not an economist and I can do whatever I want with their words. And of course, you could ask me, okay, what is the best? What is the most interesting? Are absolute deviations better than relative deviations? Who has an opinion about that?
Relative are more interesting, but you have to choose the Q, the average Q that you use for this relation.
Mm-hmm. In fact, I don't know. It's always the same when we discuss model error. Should we try to minimize the sum of absolute errors, of relative errors? I think it's two different ways to look at the same thing, and it depends on you, of course, on the expressions. As I told you, the relative has one advantage. You can try to link stream flow with temperature. You are not the prisoner of the dimensions. But if you have stream flow and precipitation, stream flow and evaporation, you can also do it with the absolute. So yes.
So I have a question. Well, in a lot of stream flow electricity, you use cubic meters per second.
Relative?
Yeah. Well, original measure is cubic meter per second.
Yes.
Yeah?
So it's cubics.
Yeah, I understand that they
cubic meter per second divided by cubic meter per second. Okay, so in fact it does not depend on the unit because it becomes non-dimensional. You know, when I transform cubic meter per second into millimeter per day, I divide by the area. But since I have the area above the area under, it disappears.
Sure, but anyway, there is area of the basin, of the river basin.
Yes.
So when will this scale problem here?
Will it be a scale problem? That's your question?
Yes. Do you discuss it somewhere?
No, I don't discuss it. So it's the right time to ask a question.
Okay. It's just it was just the question whether you discuss it somewhere.
No, yeah, I don't discuss it. So it's the right time to ask for it. So what is important to say here is if I try to so by delta first, let me explain once again what is delta. Delta stream flow. It's stream flow of year 2017 minus long-term average stream flow. So the delta is what it's often called the anomaly, or very often, I think to be more exact, we define anomalies with reference to a 30 years long period. At least that's how our meteorological colleagues define them. Okay, very often the normals, the meteorological normals are long-term average values over 30 years. So here, this is the long-term average value here, Q. How do you call it Q bar? Q with a line.
Q bar.
Q. Okay. This is the long-term average value, and this is the anomaly of 1 year or the other, with reference to this. So it's so it will be. It will be, for example, Q 2017 minus Q long term divided by Q long term. Okay? So, here, in this first definition, relative, there is no scale issue in the figures. I'm not telling that a large catchment that a 2 million square kilometer catchment behaves like a small one. But at least there is no unit problem, because if we want to divide cubic meter per second by cubic meter per second, it's non-dimensional. If we want to divide millimeter per year by millimeter per year, the area will eliminate itself. Okay, so there is no scale problem in the formula. There is a scale problem in the second formula because we need to express. Here we cannot avoid it. This has to be millimeter per year if precipitation is in millimeter per year. Is it clear or not clear? And so if I want to use no model, well, I claim you that I will present you something without a model. So of course I need something to think about the data. So I will draw a plot. And the plot I will draw will be a plot where I express as the x a variation, a climatic variation. So typically what I will show you will be variation in precipitation or variation in potential evaporation. And I will try to relate changes in discharge or discharge quantile to see how they behave, how they relate. So, and if you look at the literature, because So, those plots they are not that much. They are extremely basic. In fact, Dr. Krisanova showed us one in her presentation, but you don't see them that much. Here, if in the literature, there are two kind of plots that you find. Here, there was again the same John Shackey from the US. He had some yield change graph. So here he had percent change in precipitation. So it was in relative. And here, percent change in runoff. So, and the central line was showed the relation. And since he wanted a third dimension and have also describe also increases in potential evaporation, he was drawing several lines. So this one is for a 4% decrease in potential evaporation. This one is for 12% increase. Okay, that's the kind of line of graph we find in the literature. But the interesting thing is that those graphs are not made from data. They are made from model results. They have been thought more to synthesize modeling results. And another example, again, Wallach and McCarthy are two other famous American scientists. They were also synthesizing plenty of different climate change experiments and expressing them changes in runoff as a percentage of change in precipitation, and here change in runoff again as a function of the change in potential evaporation. So, but again, the different points, they are not individual years. They are different experiments. Which one I don't remember, but you can look in the paper. So that's typically the kind of plot I propose to do. So here is the plots which I propose to look at and try to deal with without a model. On these plots, one point represent so one plot is made. All the three plots refer to the same catchment. So there is only for one catchment where I have streamflow data over a long time period, and each point is a time period. So, and because I want to have many points, and and it's not a period of 1 year. It's a long period because I want to try to smooth a little bit the response of the catchment. So that's why I have taken overlapping period. So for example, this point corresponds to 1960, 1969. This point will correspond to 1961 to 1970, and so on. Does it make sense or not? So, and here I have made the most usual plot where I present the anomaly of precipitation in X and the anomaly of discharge. Okay, and each point, this is for one catchment. This is a French catchment. And what can you do by looking at such a plot? What can you say by looking at such a plot? If you were explaining this plot to your mother, sister, father, grandfather, who is not a hydrologist, what does it show?
If the precipitation gets bigger than the streamflow.
Exactly. The more it rains, the more it flows. And then, is it logical or not? Yes. I think that's the first thing we learn as hydrologists is that discharge is a growing function of precipitation, and if it was not that way, then we could we could question the quality of data, maybe. But at least, and the scatter is not bad. We see that there is uncertainty, but it's not a huge uncertainty. Okay, now let's look at the second sensitivity plot. So it's again the anomaly of discharge, again the same number of points, and here I have potential evaporation minus the long-term average. And so who wants to summarize this plot for his
mother, grandfather, sister, brother?
It's like less evaporation than it is more discharge. Less evaporation.
Yeah. If we have less evaporation demand, we have more discharge. If we have more evaporation, we will have less discharge. Okay? And again, is it logical? Yes. It's logical because we have to, when we look at one catchment, we are not looking at the whole water cycle at the global scale. We are not looking that with the rain that is evaporated will become the water that is evaporated here in Moscow will become rain in Vladivostok. That okay? We are looking locally at catchment scale, and at catchment scale, the more you evaporate, the less runoff remains for the river. And this one, it's my attempt to do like, I did not like Shakin's plot because it was complicated and it was not colorful. And don't forget that if you want to become a famous hydrologist, you have to first to use the word of the economists, and then you have to produce colorful plots.
But it was 1982. He didn't have color printers.
Yes. And so what did I do? I represented here the change in evaporation, here the change in rainfall, the precipitation anomaly, and the anomaly in discharge is represented in color. So, and what can you say from this plot? So it's, in fact, this plot comes to complement the two previous plots. They are the same points, but there is something else.
Just this thing? The shape?
The shape, this magical shape.
Yeah. It resembles logo of your institute.
I was thinking about it. I have no explanation for because actually there are some strange shapes. If somebody, I have 500 of those plots to show. If somebody is good in explaining magical signs, I would be glad to hear about it. No, there is something else, which concerns the quadrants. Are the points equally distributed in the four quadrants? No. And what does it mean that they are not equally distributed?
So if it's warm, then it seems there's no rain.
So there is a correlation between warmer years, or they are not years, they are here. Did I mention it? They were 10-year-long periods. The warmer periods are also the periods with less rain. The colder period, if we consider that potential evaporation give us an idea of the temperature, are also the periods with more rain. Does it make sense or not?
Depends on the climate.
It depends on the climate. So the true answer.
Sorry.
I did not expect less from you, but the true answer that is that for France, which is, in fact, since I'm not specialist of tropical climate, I cannot tell you. In France, usually it's well correlated. The years with very large precipitation, you have more clouds, more cloud cover, probably less temperature. And there is also, there can be also other climatic reasons that only a geographer can explain. I'm not a geographer, I'm just a simple non-geographer hydrologist. Okay? And I don't know how it would be in Russia. What do you think? Did any one of you look at long time series?
Could give an assignment for tomorrow.
Assignment for tomorrow, exactly. Who wants to take?
I'm sorry, I interrupted you.
I'm just trying to say that Russia is really big and just all zones just have different plans. Like if you take Vladivostok, it's depends on movements from Pacific Ocean. If you take like central region of Russia, it just depends on
Okay.
the ocean and so on and so on. So
Who has a long series of potential evaporation, precipitation, and discharge under the hand? Who wants to take an assignment to do the graph for tomorrow? Nobody has something ready from his or her PhD? We don't want permafrost. Next time.
Okay. So, and because there is this correlation, so we see that we see first that there is a correlation. So there are more points in in the first quadrant and in the third. And where are the green, the redder points? They are there. I mean, once we have both the effect of precipitation, of decreased precipitation and increased evaporation, we have very strong anomalies. Okay, this all makes sense, and in fact that's where the whole difficulty of those ends. I mean, I have nothing more complicated to tell you, except that of course we take periods, and we could ask ourselves what kind of period length we would like to have. If we take those are, so remember the graph is precipitation, evaporation, and combined. If we take very long period to aggregate, what do we see?
So all points represent the same time series.
Yeah, because I don't have an extremely large time period, and also because averaging reduces the variability, and I don't see much. So it's this averaging over 20 years is not what I want to see. On the opposite, if we look at those are individual years, what do I see? There I have a large scatter. That's where I have the most scatter, obviously, but
Still there is correlation.
there is correlation, but there is a lot of noise, I would say, in the. So, as a statistician, you may not be annoyed by noise, but don't forget that you are not when you walk around it outside of this building, you are not surrounded by statisticians. You are surrounded by people who have been taught that correlations are made by points that are perfectly aligned, and they will not like that. And also the fact is that the catchment is not it's not a parking spot with no memory. A catchment has soil. A catchment may have groundwater, and soil has a memory, brings a memory to the catchment. the snowpack also. But of course, if you are in Russia, you are not going to cut your year in the middle of the snowpack season. You will take a hydrological year. And but groundwater has a memory that can last for several years. In exceptional catchments, it can be much longer even. That's why that if we want to have compensations, to avoid those compensations, there is some interest in averaging a little bit. So, and if you take either 5 years or 10 years, you see that lines become more straight, nicer, and so you have to avoid the extremes, and then between extremes, it's up to you what you want to, what kind of aggregation you want to work
Would
with.
this 10 years be related to 11-year sun spots period? Maybe there is a long-term variability. You know, sun activity is 11 years.
As I told you, I'm not a geographer. I never heard about those sun cycles.
Okay, let's think about this.
But it may be. No, usually 10. It's because as a child I learned to count on my hands, and usually I like the number 10.
May I ask, why do they converge to such kind of spot with 20-year average?
It's because it's an anomaly. It's because they all collapse because there is no variability. So basically, since I computed the long-term average with all the data, they become the same thing.
And on 10 years, why do you have these two lines you see here? As if there are two clusters of data.
I don't know. I would like to know it. It looks.
Assignment for tomorrow.
Yeah, it looks. In fact, first before I tell you what I think. In fact, I have no answer. Does any one of you have an idea? What does it remind you? This? It looks like some hysteresis. And this hysteresis, where do you find in hydrology hysteresis? Don't answer. Excuse me? Where do you?
Discharge and the level in springs. Water discharge.
Water discharge and?
Discharge and level of water in springs.
In rivers. In the rating curve, is it right? Are you talking about the rating curve? Okay. So this is, you all know what is a rating curve. What was the Russian for it? Krivaya? Epatage? So it's epatage? No, it's true or not? Oh, it's a joke. No. Don't make jokes with me in Russian.
Кривая расхода.
Krivaya rashoda. Okay, krivaya rashoda, it's how discharge is depending on at one gauging section. So what do we do to build this curve? We go in the river and we make manual measurements of speed of the river. We get 1 point, and then when we have many points, we get some curve which is something like that. Okay, so this is the typical one on nice rivers, and there are bad rivers. The bad rivers gives things like that. Okay. So, but this is a bad river, but there are many sites where you cannot avoid. So, in fact, what does it mean? It means that when in the hydrograph during floods, when water rises, it goes that way, and water decreases, it goes that way. Okay? So when you try to put a new gauging station, you want to avoid that. So it's not hysteresis let's say discharge stations are not what you are looking for, but sometimes you have no choice. When there is, the hydraulics in French we said contrôle aval, downstream control. Does it make sense? Who is hydraulician here? So when there is downstream control on the relationship, that's what happens. Okay, so
Like, when something maybe pushes the level up from the downstream. Right?
Okay.
Yeah.
And so there are other examples of hysteresis in hydrology, and it's very common in Russia in winter. What happens in winter in Russia?
Ice jams.
Ice jams, yes, but I was not talking about ice jams. Not about what happens in Russia. I did not hear. Snow cover. Okay. So if you try to link, you know that what is easy to measure is the height of the snow, of course. But what we hydrologists are interested in is a snow-water equivalent. Okay? So if you try to draw snow-water equivalent as a function of height, then you obtain something like that. And yeah, in the fall, when you have in the fall you have Ludmila, help me. What happens in the fall? In the fall you have less snow is light, less dense. So it's which one? This one or this one?
The right one. Right
Yes.
one.
So at equivalent height we have less water.
Yeah.
Okay. So this is fall, and then this is spring med. Okay. It means that if I go and make a measurement in the fall and the spring, I measure exactly the same height. Does it mean that there is the same amount of water? No, because there is again an hysteresis in this. So hysteresis, it does exist in hydrology. So it's a nice word to learn. And how do you say? Do you say hysteresis in Russian? So here it looks like a hysteresis, and who knows why. So I don't know, so I would like you to make me suggestions.
If it's changing the government, then policies in agriculture change.
It's Macron, Hollande.
Yeah.
Well, I would like to know, because in fact I think I show you other. No. So I did the plots for those. This is France, sorry, and France is it's not a very large country, but it's almost 550,000, 500,000 square kilometer. Russia.
Only?
It's large. Do you want?
No, I don't. Sorry, excuse me.
And so those are. I had a large catchment set with many rivers with long time series, which are of reasonable quality. So don't forget what I said this morning. There are no perfect measurements, but as a modeler, you should not start criticizing the measurements. Let those who are in charge of making the measurements, who criticize their own work, then take their work, and if of course they don't do it perfectly either, but don't start at least with it. So I consider they were good quality measurements, and that also the level of no, I mean there were no large cities, no large dams, because it doesn't make so much sense to do this. But there were not complete natural catchments, but normal French catchments. Okay, and I did that, and I produced a lot of those plots. So, and you can see that in fact the first. Oh, I forgot. This one is again a catchment with a positive relationship between precipitation and discharge, and almost no relationship between potential evaporation and discharge. And that's what you see. The red points, they are not in this quadrant, they are just below the line equally there and there. So what does it mean? In fact, I don't really know. I mean, the hydrological good sense tells us that probably this relationship is more direct than this one. So this one should be strong and this one weaker. And there is no reason why it should not happen. So maybe it's my measurements. Maybe it's the potential evaporation formula which I'm using, which is not the most adequate. I used the Penman-Monteith FAO 56, which is maybe not good. But at least when you use it, you tell people FAO 56. It looks like it was you are very smart.
But maybe it's potential, not actual. So maybe there is no water to evaporate.
Right, but don't forget that I always use potential as a measure of the demand, because perhaps it's a more. Of course, we don't have very arid catchments. It could be a very arid catchment. On an arid catchment, what will we have? We have quite no sensitivity to potential evaporation because we are always lacking water to evaporate. Okay. And this is another very good, well-behaving catchment, up, down, and I have many of those. So now I had promised to. Do you want to stop 5 minutes?
I do, I know.
Yes, no break. 5-minute break?
Yes. Before the break, so I promised that I will give you a solution without a model, and that's where I tell you that I lied a little bit, because without a model I can give you plots, and if we want to go a little beyond plots, we need a very minimalist model, and I will ask you what model you propose for that. So we're starting again. So remember, I told you that this figure is worth any model, and it allowed me to do a prediction on the impact of climate change. If the IPCC tells me that on my catchment I will have 100 millimeter more precipitation, I can with rather good confidence say I know what will happen in terms of stream flow. The same for potential evaporation. Of course, the problem is when IPCC says something here, I have to do an extrapolation. And extrapolation are not easy, but they are not easy for my graph, they are not easy for the models. In fact, extrapolation is the most difficult thing in hydrology or in science. So, but if we want to quantify things, and also I told you that I have 500 of these plots, showing 500 plots one after the other. It's possible. Now we have computers and produce the plots automatically. It's very nice. You write. When I was a student, you had to produce a plot. You take a hand, a mouse, and produce each plot differently. Now you can write a small line of code and you produce a 500-page PDF, and you just have to show it to your advisor, who says, "Good, do some other ones." But in the past, it was more time-consuming. I'm not even talking about the time when you had to produce a plot by hand. So if now we want to synthesize, what do? We obviously want to do the simplest model that we have learned as hydrology, is a regression model. So there are several options for regression. For the first one, which is purely mathematical, is we have either to use ordinary least square or generalized least square. No, ordinary least squares and generalized least squares. And this is because we use moving averages. So that's what I was explaining to some of you. We produce averages. This is the time when we produce averages on overlapping periods. So those periods cannot be considered independent from each other. So the we should account in the model the fact that they are not independent, and that's what allows the generalized least square method. And obviously I've tried both, and this one is slightly better. And if you don't want to, if you are tired or you don't know how to use this in the software package you are using, but you can try simple regression. Okay, but this one is more exact. Then obviously you can try regression independently for either streamflow as a function, streamflow anomaly as a function of potential evaporation anomaly, and streamflow anomaly as a function of precipitation anomaly. You can do it independently, or you can write a multiple regression with both at the same time. Okay, you can either write it's either y equal to ax plus b, or y equal ax plus b or z plus c. Okay, you can have this 2 in a row. All the 3 together. Is there a difference? Does my question make sense, by the way? Did you understand what I was proposing? Should it be a difference? Because I started to tell you that you have 2 options and they are more or less the same. Here, if we deal with precipitation first and then with evaporation, will we have a difference than if we deal with them all together? The answer is it depends whether precipitation anomalies and evaporation anomalies are correlated. Okay? And are they correlated? In France, yes. So you should not do it independently. You should do it simultaneously, because the simultaneous accounting allows you to account for this dependence. And then, of course, you have to decide of a period length. So, as I told you, you can do it with any period length. If you average over 2 long periods, you will have almost no variability. If you have maybe year by year, may have some noise. So it's up to you. Have to take a decision depending on your catchment, on what you are. Okay, and so the alternative. Those are the 3 alternatives, 3 regressions. This is the simultaneous. This is the independent regression. And I told you that this is the one you should, because this will give you, because of the correlation between evaporation and precipitation, this will give you results that are much more, much stronger dependent sensitivities than here. Yeah, and that's because this graph that we discussed in length, there is a correlation. The worst case usually are when both evaporation and precipitation are evaporation is increasing, precipitation is decreasing.
Could I have a question?
Yes.
And what if you calculate effective rainfall? And then do single variable regression?
So effective rainfall, how do you take a model to compute effective rainfall, or do you take P minus
P
potential
minus
evaporation?
Potential, but if you have maybe actual.
So in fact, with actual, the ideal would be to have, how do you measure actual evaporation, by the way, you students? Evaporation plot. Well, how is it named, the evaporation plot? As a hydrologist, I measure evaporation with a catchment. But that's what we do. But what is the alternative? You had some huge one in Valdai, maybe in many other places. The Germans are very fond of it. It starts with L. Lysimeter. Okay? Lysimeter is you have a huge bucket full of soil that is weighing the soil amount, and then you have some sort of measurement of actual evaporation. Okay? So in fact, in answer to your question, the ideal would be to try with the data of a lysimeter, long-term lysimeter. That's a very good idea. In fact, I have some on my computer, which a colleague gave me, but I went 2 years ago. I did not find time. See, if somebody wants to do a nice plot tonight, nobody wanted to do the assignment. So now, this is synthesis. So again, this is France, and here you have the elasticity to potential evapotranspiration, here the elasticity to precipitation, and I have a scale where the reddish colors are for negative. Negative means the more evaporation, the less runoff. I am interested in runoff. Positive, in the blues, it means the more precipitation, the more runoff. The small crosses is when it is considered as not significant. So there was some significance test. And since I did not do the significance test part, I cannot tell you. I don't remember what it was. I have to look, so I'm not saying. But as you remember, we saw some plots there where obviously we can compute some regression line, but it's not significantly different from 0. Okay, so that this is to account for this kind of catchments. And so, what do we see? So we see that France is a beautiful country. It looks like a hexagon. That's what we learned at school. Now, if we look at the number of crosses first, we see that there are a lot of crosses here and very little crosses here. What does it mean? So remember, this is evapotranspiration, potential evapotranspiration sensitivity, and your precipitation sensitivity. And there are more crosses northwards also.
So stronger link to precipitation.
Stronger link to precipitation. Is it what you would expect? Yeah, I mean, if your first year of, or maybe your first course of hydrology, I think you have been told that streamflow is a function of catchment area. The first huge, and the second is precipitation. And then we start to discuss the rest. So that's basically what we see, so it's not surprising. The other thing is, it could be also that we have more interannual variability of precipitation than interannual variability of potential evapotranspiration. If you look at the changes, I mean, in France, we can have rainfall ranging from, of course, no, it has nothing to do. On one catchment, for example, I take the Paris station. Paris station, the lowest precipitation was in 1921. It was 400 millimeter, and the highest in 2000, it was something like slightly above 1,000 millimeters. So, and the average is 600 and I don't know, but 50 maybe. So it's by a factor of 2. You never have changes of temperature or and the potential evaporation by a factor of 2, at least in France. So this is much more variable than this one. So obviously, when we have a greater span of variations, we get nicer regressions. So this is also also something true. And then you see a couple of outliers. Do you know what are outliers? An outlier is a point that is the French used to call them point aberrant, which means aberratia. But I think that the French way is not the right way, because it's not scientific to call those points aberratia. It's the fact that they are not like the others. It's true, but maybe there is something to learn from them, and sometimes there are also measurement errors. So we at the end we can consider sometimes measurement errors or problems. And so here I see one aberration with a blue point, where on this catchment it seems that there was more potential evaporation and more stream flow. So and obviously it should be not significant, but it turned out to be significant. So it's a point high in the mountains, in the Alps.
Is it snow control?
It is snow control, but in fact, the only French glaciers are here. In fact, I wanted to look at this point again and to show it to you, and I did not. But the only French glaciers are in this area, on the Arve River, which flows then in the Lake of Geneva. So it may be some glacier influence, and on glaciers, that's a very good point. In fact, I did not. On glaciers, we have an opposite relationship. So on glaciers, because we have a huge stock of, stock is English or not? No, it's not storage of. We have stored water, and if you increase the temperature, you will get more flow. So obviously, this is a good explanation for this point. You will get more flow for a few years, and at the end, nothing. That's another story. Okay, so you see small aberrations, but not that many. Don't forget, a plot without any aberration is a plot that has been what? That has been manipulated to get rid of the aberrations. When you have 500 points, it's impossible to have not a single aberration. So if the plot is too clean, it's like when didn't you notice that in the magazines when you get mod photos, the models, they have not a single women or men. They're just perfect, and not any small imperfection. What is the reason for that? Photoshop. Okay. So scientists also have, some scientists, not the good ones, I would say, also have the habit to Photoshop their data sets. So they don't Photoshop them. They exclude the bad points. But the fact that they include the bad points doesn't first, it does not mean that the bad points did not exist in the first instance. And then for example, I did not think about glaciers, but glaciers is a very good explanation. It's a physical hydrological explanation. It would, if I had suppressed by Photoshop this point, I would not have had the occasion to discuss about that. So I learned something because I did not Photoshop my plot. And then I could use these elasticities to give predictions. I can either, let's say, trust individual point for individual catchments, or I can try to compute regional average values for those and propose these as predictors of future changes. Okay? And then it's always interesting when you know well the area where you work to try to find also some regional explanations. Here, of course, you don't know France, so you don't know the regional explanations. There are here some points where, surprisingly, we have very light color, so it's less dependent on precipitation. And this is the area of choke aquifers in France. So there are choke aquifers famous in France and in Great Britain, in the Thames River Basin. In fact, it's the same geology, exactly the same formations. In fact, the Thames, before the water raised, the Thames was just part of the same basin, and not the opposite. Anyway, and so this probably have to do with the fact that those catchments their flow is much buffered by by groundwater contribution, and so it's buffered, but it's one of the difficulties because it's like the glaciers. When the glaciers have melted, what will happen here? It will be, when the effect of the glacier will have disappeared, it will behave like the others. Here, probably once the groundwater, in case of extreme change, will have lowered, it will not be any more connected to the river, and the catchments here, which are less dependent, less reactive to precipitation changes, will just behave like the others. So my first conclusion is how much time do we still have after that? Half an hour?
Or more like 10 minutes.
Okay, then my first conclusion was that we'll do this. In fact, in the 1989 paper of Chaki, I look at the conclusion, and in fact he was concluding the same as me. Water resources are more sensitive to precipitation change than to potential evapotranspiration. So I did not invent anything. I just confirmed what they had found. And now, the second part, I had promised you simple things and then a little less simple thing. And I also, Alexander Yelfond also wanted me to give credit to Russian scientists. So I need to do that for, and now we are done with plus. Let's consider that what we have done was looking at plus. And we are going towards model, but not reaching complicated models. And there is some intermediary, very low complexity models, which are the water balance formulas. So, what kind of water balance formula do you know, by the way? Do you know any water balance formula? So by water balance, I mean I want discharge for long term. Okay, it's as a function of what? Okay. All for long term. So there, we have no time series. So we want one formula, one figure by catchment. What is the simplest that you could imagine? Of course, it would be a linear one. Okay, you can try this, and from at the beginning of the 20th century, they were already producing that kind of formula. So you can have A P plus P. You can have A P plus P potential plus C. You can have or any kind. It does not need to be linear. You can have A, P at the power of B. Okay. Do you know any of those formulas? Did you learn any of those? What, do you know the name of it? No. Well, there is one quite famous. It was a Russian academician, climatologist, but he was not a geographer. That's why you don't learn about him. Budiko, yes, he has a formula, which is quite complicated, by the way. It's not the most interesting. So here we have different type of formulas. The oldest formula, the oldest were that kind of formulas, but the most interesting for me is from the old ones is the one of Oldekop. Oldekop was Estonian. And by the way, his PhD or master thesis is in Russian. Very interesting read. So he was from the University of Tartu. And Oldekop, and of course, I am interested in streamflow, so I express there is a streamflow formulation, and those who want the actual evaporation, they have the equivalent. We write Q equals P minus actual evaporation. So this is a formula with the hyperbolic tangents, and here this ratio P divided by potential evaporation. How do we call it? No, how it's known in the literature. It's inverse. Potential evaporation by precipitation is aridity, and this one often we call it humidity. But in France, sometimes they call aridity, although it's the same. So it's a formulation that relates discharge to aridity. Here, that's where the Turk was French. So Lucien Turk, he was French agronomist. In '54, he published the same formula as Varfolomei Mezentsev, produced in '55. So, and he was a geographer. You should be proud of. He was from a geographer from, I think, the University of Irkutsk. Of course, if it's not NGU, you are not interested, I guess. Okay. And again, it's a formula, and here there is no parameter. Here there is one parameter to representative of it, and basically it states that the actual evaporation is equal to some harmonic average of actual precipitation and precipitation. So the harmonic average, you all know, it's the average of x and the harmonic average of A and B is 1 over A plus 1 over B. Okay? And here it's I don't think that there is a name for it, but it's generalized in the sense that there is a power. Okay? And then we write Q equal P minus actual evaporation. We get discharge. And there is another one which also has one parameter, which is almost the same, but you can try it with the math and try to equal them. You will not find the way. But you can show it numerically that they are almost the same, but not analytically. And it's a formula that has been proposed by a Frenchman, Tixeron, and later published by a Chinese named Fu. And since the Chinese are much more productive, you know, all the Russians complained that there were famous Russian scientists in the 50s, but since nobody read Russian, now they are giving to foreigners the paternity for formulas that had been invented by Russians. That's the same with the French. Since nobody read the French, Tixeron, all the hydrological community called it Fu formula. I knew that at least you would understand us for French. So there are the three most famous formulas. So Boudico derived his formula from Oldekop, but basically the Boudico formula, it has a hyperbolic tangents, an exponential, and then a square root. It's completely stupid the level of complexity it has. This one is very simple. It's just let's say almost harmonic mean. And if you want to, you can also, often it's not expressed in this way, it's expressed in relative term. Water yield is a function, it's exactly the same. This one and this one, you express it, water yield is a function of humidity index. Okay? It's the same. So why is this formula interesting? First, because it is simple. Then, because when you plot the data for a large number of catchments, you see that it does represent quite well the variability that you encounter in nature. And also because we can compute analytically the partial derivatives. And the partial derivatives are the sensitivity, or the elasticity, as I called it. dq as a function of d-rond q. How do you say d-rond? Round d. Partial derivative of q over p, partial derivative of q over potential evaporation. So, of course, there was one parameter, and this parameter remains there. And if we plot those, what do we have? Here I took the Turk-Mezencev formula, and n is 2.5, because in French it's the average of n. Try to compare with data. But the n that fits the most with the most French catchments. Then we see the elasticity of discharge to precipitation and of discharge to potential evaporation. What do we see here? So this is the humidity index. So here are arid catchments, here are very wet catchments. Okay? The more we go toward the right, the more humid we are. And here is the sensitivity. What can you say about arid catchments? So the line 0 is there, sorry.
No water.
No water, you can change a little bit precipitation. There is the arid catchment, they are characterized by there is a huge unbalance of evaporative demand over precipitation. So if you add a little bit of precipitation, will it change something in stream flow? No. Does it make sense or not? That's what's interesting in this graph, is that we can discuss the sensitivity. I take, what is the definition of an arid catchment? An arid catchment?
Have like dry soil that is need like water, and first of all water going into soil before just to
Exactly.
evaporate.
So, aridity, we defined it, or the geographers defined it as a ratio between potential evaporation and precipitation. If it's very arid, it means that there's a huge deficit of precipitation. So, you add, it's like, if you, no, I was going to find, I was going to find an economic comparison, but
If
no.
there is no money of population, whatever you offer, they wouldn't buy because there is no money.
Yeah. Or no, if you want the Russian people to buy cars, you take the poorest of them, you give them 200 rubles. How much increase in car sales does it produce? Zero, because you don't buy a car with 200 rubles.
No, I can buy a ladder. I had a ladder 44 years old.
44 years old, how much do you pay for it?
It was from my family, so
Okay. So it was,
7,000 rubles.
no, but it had an immaterial value.
That's true.
then.
That's true.
We cannot measure immaterial value. So do you agree now? As I forgot your name, Dimitri. Wait. As Dimitri said, on a catchment, in order to produce runoff, you first have to satisfy. Rain does not fall directly on the stream. Very small portion. Rain has to go through the soil or to run off or to go into flow. And if there is storage space, if there are hungry plants ready to intercept this, I mean, nothing will get to the river. So on arid climates, the sensitivity is zero, because whatever you change, it will be taken by others. Then when you move to our less arid climates, you get an elasticity which is positive for precipitation, negative, which is always positive for precipitation, always negative for potential evaporation. Is that normal? Yeah, that's the formula is well has been well written. And when you get to very wet climates, what happens? The sensitivity is almost -1 for potential evaporation and almost +1 for precipitation. Is that normal or not? Yes, it's normal. Why? Because you have already so much precipitation. You have 3 times more precipitation during the year than potential evaporation. Then all the energy that could be used for evaporation has been used already. There is no energy left to evaporate water. So what happens when there is no energy left to evaporate water? It infiltrates, and then if it cannot move from, if it cannot leave the catchment by the atmosphere, it will leave the catchment by ultimately by the river. Okay? There are 2 exits in a catchment: the atmosphere and the river. In fact, there is a third one. It's the groundwater, but let's consider that no really groundwater flow. Okay, so this is why the sensitivity is 1 here, and again here there is almost all the potential evaporation has been used. All the available energy has been used. If you give a little bit more, then it will be used almost immediately. Okay? That's why we reach the limits, the mathematical limits, -1 and 1 here. And of course, I told you there is one parameter here. I tried two different parameter values, and it will give you slightly different behaviors. Okay. And the conclusion. Is it time to conclude? The conclusion is that with simple water balance formulas, we also have the possibility for some analytical computation of streamflow elasticity. So the Türk-Mesencev formula has a single parameter n, and it's very attractive for that. And it's a beautiful. It was, let's say, conceived simultaneously in France and in Russia. What a wonderful friendship! And they did not know each other. Wonderful. Of course, are there limits? Yes. The limits are that with any model, even the most complicated model is a simplification of reality. So the simple water balance models are also, of course, simplification of reality. So, for example, n, it's not sure that it can be considered independent of climatic changes, because when you look in detail, there is the seasonality of precipitation and evaporation plays a role, and then no model is perfect. And we had written a paper 2 years ago on climate elasticity with my colleagues that I want to acknowledge for their work. And believe it or not, I discovered that there is a painting by the famous futurist Italian painter Umberto Boccioni, which is called Elasticity. And on that I am finished.